In particular, I shall speak today about connections with modular and distributive lattices. In the second part, I shall present some results about a class of finite order generated hyperrings in which hyperoperations induce set-valued join and meet operations compatible with multi-lattices. And these connections was established starting from the multi-lattice axioms in the Benado sense, and we also provide some illustrative examples. Finally, I shall present some ideals and filters and show how different hyperrings may induce the same multi-lattice structure. Okay, so here there are some definitions about semi-hypergroups, hypergroups, Jones spaces. Some words about the Jones spaces. First of all, I recall the definition of a Jones space. It is a kind of commutative hypergroup such that the following implication is satisfied. We denote first by A/B the set of all elements X of H such that A belongs to X times B. And we wish this condition is satisfied, which means if the intersection between A/B and C/D is non-empty, then AD intersection BC is non-empty. It can have a geometrical interpretation, this condition, join because these sets have non-empty intersection. This notion was introduced by Prenovitz, and after Prenovitz and Gentoschak applied that notion in both Euclidean and non-Euclidean geometry. They use this notion in order to describe descriptive projective spherical geometries. But not only. Jones spaces can be studied also in connection with binary relations, fuzzy sets, or rough set. First of all, very intuitive example. If we start with an equivalence relation denoted by R, and we denote the equivalence class of A in this manner, the class equivalence class of A, we consider as a hyperoperation the product A times B is the union of these equivalence classes, and so we obtain a Jones space. Or another example, if for all X elements of a commutative group G, we consider a not empty set A of X such that for different elements X and Y, A and X and A and Y have the intersection, the empty set, then we consider the union of all A of X for X element of G. And you use this map F. The map F has this property, F of A is X, if and only if A is an element of A, capital A of X. We can define this hyperoperation, this new hyperoperation, A square B is this set, capital A of FA, FB, and in this manner we obtain a Jones space. But many Jones spaces can be constructed. Another one, this is just an interesting type of Jones space. We start with a hypergroup and we construct a new hypergroup, actually a Jones space T, using a family of non-empty subsets A, I is an element of G, such that A1, the one is identity of the commutative group G, is H. And for I and J different elements of J, capital A I intersection capital A J is the empty set. Then we consider the union of these subsets, and for AB in H, we have just the usual composition defined on H. If A is H, is just capital A1. And for indexes AJ, such that at least one is different from the identity, A times B is capital A index K, where K is the product IG. And in this manner, we obtain a joint space if and only if H is a joint space. So is a way of constructing a new joint space starting from a hypergroup, in particular from a joint space. Connections with lattices and the ordered set was initially made by Jean Mitas, and then by Maria Constantinidou, Carlos Serafimidis, Christos and Gerasimos Masuros, and later by Kehagias. But also they were studied by Chvalina in Czech Republic. The above mathematicians were all from Greece. The Greece school studied hypergroups, lattices, also hyperlattices. In what follows, we present some of these connections with two important classes of lattices, distributive and modular lattices. First one is about connection with the distributive lattices. We consider here as a hyperoperation just the closed interval. So we consider all elements X of the lattice such that X is between the mid and the join of A and B. And a famous result established by Varlet says that a distributive L is a distributive lattice if and only if L is a joint space endowed with the above hyperoperation. Together with Ivo Rosenberg. Ivo Rosenberg was a famous mathematician from Canada. He passed away some years ago. I consider and analyze with him a family of hyperoperations. We put here two indexes, P, Q, and we define a family of hyperoperations where A times PQB is the closed interval A meet B meet P, and A join B join Q. So these two elements, P and Q, are used now in order to define the new family of hypergroupoids. And we notice that if we start with a distributive lattice, we obtain a joint space for every P and Q. Another situation, we can consider a modular lattice, and a Japanese Nakano studied this hyperoperation. It is not just necessary to be a lattice. To start with a lattice, we can start with a semi-lattice and have, for instance, only join. Or dually, we can consider the mid. But for join, we can define A time B as the set of all elements U such that the join between A and B is equal to A, the join between A and U, and equal to the join between B and U. Notice that this set is non-empty because supremum of A and B belongs to this set. So if we consider U equal to the supremum, we have an element of this set. And an American professor, Comer, showed later that L is modular if and only if we obtain a Jones space using this hyperoperation. So Jones spaces are useful in order to characterize these two types of modular lattices. Also for the second hypercomposition, I and Rosenberg defined a family of hypercompositions defined in this way, starting with an element P of L, and whichever element P and L. We also consider particular cases for P. And if we denote LP, the set of all elements bigger or equal than P, we obtain that LP is modular if and only if L, endow it with circle P, is a Jones space. Another connection made by two colleagues of mine from Alikuza University, Professor Tofan and Wolf, they start with a lattice and they consider this hyperoperation, which is similar with this one introduced by Varlet, and also similar in the context of fuzzy sets with hypercomposition introduced by Corsini. So Corsini used, instead of F, a fuzzy set. So L is the closed interval 0, 1. Here, instead of consider the closed interval 0, 1, we consider just a lattice. And infimum and supremum, we use these two notions in order to define the hyperoperation. And we can obtain a commutative hypergroup. Moreover, FL, the image of L, is a distributive sublattice if and only if the hyperoperation satisfies the Jones space condition. Also, this happened for the particular case of a fuzzy set. So when L is equal to the closed interval 0, 1. Professor Corsini introduced this hyperoperation. Just to say some words about him, it was my collaborator for decades. We wrote a book together about hypergroups and applications. And he helped me very much in doing research, in learning me to do research on this topic. Now, some words about another important class of hypergroups, canonical hypergroups. They are actually a class of Jones spaces, and they were introduced by Mitas. Mitas was another pioneer of hyperstructures. He introduced many types of hyperstructures in connection with ordered set, with lattices. And they studied canonical hypergroups as an additive structure of Krasner hyperrings. Krasner hyperrings represent a class of hyperrings which are near to the rings we know. We have only one hyperoperation, that is addition, but multiplication is just an operation, not a hyperoperation. This structure of Krasner hyperrings were used by Roth to obtain results in finite group character theory. And McMullen and Price studied finite abelian hypergroups over splitting fields. More results about canonical hypergroups have been obtained by Christos and Gerasimos Masouros, in connection with automata theory. By Corsini in connection with SD hypergroups, Herapimidis in Greece, Constantinidou, Mitas again. Feebly canonical hypergroups were analyzed by Corsini and Mario De Salvo. Canonical hypergroups are exactly Jones spaces which have a scalar identity. What does it mean, a scalar identity? It means an element E such that for all U, we have U times E equal to U, and also equal to E times U, since they are commutative. More general structures were be considered then, namely polygroups, which are also called quasi-canonical hypergroups. They were studied at the beginning by Bonansinga, Corsini, Masouros, and I learned last day about our colleague Madeleine Altahan also nowadays. Comer analyzed polygroups in connections with graphs, with relation, Boolean, and cylindrical algebras. And the particular polygroup, the polygroup of bilateral classes, was investigated by Dirbolov, Harrison, and Comer. They satisfy the same conditions as canonical hypergroups, with the exception of commutativity. And now I wish to present some of my recent results about hyperrings and multilattices. I introduce a class of hyperrings that I call order-generated hyperrings in order to have a connection with multilattices. Multilattices are very old. They were introduced by Benado, a Romanian mathematician, in 1955, but only as purely order theoretic structure, and he studied these structures. In a multilattice, we have a set of minimal elements. Instead of having supremum of two elements, which is the minimal upper element, the minimum between the upper element, not the minimal, but also minimum, the minimum, we have here minimal elements. So instead of supremum, we have minimal upper elements, upper bounds of a subset B. And similarly, we have maximal lower bounds of B. So we have here sets, not just supremum and infimum. A joint multi-semilattice is a poset, so poset ordered set M, in which for all elements A, B, and X of M, such that X is an upper bound, so of A and B, there exist a minimal element of the upper bound, which is z, which is smaller than x. So it is minimal because it is smaller or equal to z. In the dual manner, we define the meet multi-semi-lattice. And we have a multi-lattice if it is a join and a meet multi-semi-lattice. The notion of hyperring originates, as I said, from the hypergroup theory and later from the Krasner researches. So Krasner introduced a type of hyperring that he called Krasner hyperring, and also we call today Krasner hyperring. And they have many applications in algebra, geometry, fuzzy structures. My most recent book about hyperrings is called just Krasner Hyperrings. It was written with Professor Davas in 2024. Because I said already some words about Krasner hyperring, we can say also the definition. So as an additive structure, we consider a canonical hypergroup. Each element has a unique inverse. 0 is a neutral element. And concerning the multiplication, it is a binary operation. Distributivity holds a connection between these operations. And sometimes we can have an identity element for multiplication. Here is an example. You see for multiplication, for addition, we have a commutative canonical hyperring, canonical hypergroup, And for multiplication, we have just an operation. And what about these order-generated hyperrings? So we start with a multi-lattice. So for each two elements, we have a set of minimal upper bounds. And similarly, for the lower bounds, we have a set of maximal lower bounds. And we start with M from multi-lattice, a non-empty set, and do it with an order. For join and meet, I consider these sets. So X is a minimal element with this property, while Y is maximal. And if join and meet is singleton, we obtain a lattice. This properties holds for M since we start with a multi-lattice. So we have idempotency, commutativity, anti-chain property. What does it mean? It means that if X and Y are upper bounds and or of A and B, so upper bounds, and we have an order X smaller than Y, then must be equal. So we can have chain structures in the set of the minimal upper bounds of A and B, and similar for meet. And a so-called M associativity. Actually, this property holds for any elements A, B, C. Okay. And so the definition of order generated hyperrings. Hyper operations and identities. About hyper operations, they are commutative. 0 is additive identity, and we consider also 1 multiplicative identity. So we need both of these elements. A partially ordered set H. And it is interesting that addition, so when we consider the addition, produces only upper bounds of the elements A and B. In other words, all elements of the A plus B are upper bounds of A and B. And also it contains minimal ones, the minimal upper bounds. And similarly for multiplication. Multiplication contains lower bounds and contains the maximal ones. And I impose here as a connection the quasi-distributivity, which means a weak condition, as Thomas considered, why it is useful. We must have a connection between addition and multiplication. But on the other hand, if we consider distributivity, a multilattice become just a lattice. So we need a weaker condition. And I present some examples for addition, this table, but we shall see also the representation. And for multiplication, this one. The order is this one, x smaller than y, x and only if and only if y is an element of x plus y. So it's, as I said, addition produces upper bounds of x and y, so x is smaller than y. And using these tables, just a moment, I shall come back, we obtain this diagram. So you see here, we do not have just a supremum for A and B, but we have a subset composed by C and D of a subset of which stays as a supremum of minimal upper bounds. These are minimal upper bounds. Upper bound is also 1, but it is not minimal. Similarly, for C and D, A and B are maximal lower bounds. Also 0 is a lower bound, but it is not a maximal. So this is a very intuitive example of a multilattice, and it represents the hyperring given above, which is a connection now. If we start with a finite order generated hyperring and we consider as join only the minimal elements which are upper bounds, and for mid maximal elements which are lower bounds, we obtain a multilattice. The hyperring has already an order. So respecting this order, it is a multilattice. And for that example, we obtain just this diagram. Another example. But if we consider in this new example here, the addition, just the set of minimal upper bounds, and multiplication the set of maximal lower bounds, so the tables are reduced to this form. They are less multiple valued hypercomposition for the composition of two elements, just few. And we obtain an order-generated hyperring. Another example constructed also on this set of how many? Of 6 elements. A, B, C, no, this is 7. No, this is an example for a set with 7 elements. Okay, and we obtain this diagram for the associated multilattice. Okay, I just give an idea. But we notice that we can have more hyperrings that are associated to the same multilattice. And we shall call one of them, which one I shall say, the representation equivalent. First of all, two hyperrings are called representation equivalent if they induce the same multilattice. But between these hyperring structures that they induce multilattice, we shall consider one that we shall call canonical hyperring representation of a multilattice. And for this one, we consider not for addition, not all upper bounds, but only the minimal upper bounds. For multiplication, not all lower bounds, but only the maximal lower bounds. And in this manner, we obtain a so-called canonical representation for a distributive, quasi-distributive multilattice. So the quasi-distributivity of the hyperrings is transferred to the multilattice, so the multilattice is quasi-distributive. Okay, every quasi-distributive multilattice admits a unique minimal hyperring representation. Some words about ideals and filters in these multilattices. Similarly, as in lattice theory, we can consider the filter notion, and the conditions are just similar. Instead, if X is an element of F and Y is bigger or equal than X, then Y is in F. And for all mid-closure, for all X and Y elements of F, every element of here, there is a difference because here is a subset instead of being just the mid, X mid Y, we consider every element of this set. This set is a maximal lower bounds of X and Y. And dually, we have the notion of an ideal for a multilattice. These definitions are not introduced by me. They are because the multilattices are studied since 1955. I only wish to see what does it mean, what is the correspondent of these notions in the hyperring structure. And a filter corresponds to a subset of H which is closed under hypermultiplication and upward closed with respect to the partial order, and dually for ideals. And I give an example for one of the multilattices considered above, Z1 of 7 elements. An example of a filter of ideal. And we can speak about morphism of these order-generated hyperrings. I put conditions for addition, for multiplication, since both of these rings contain 0, 1, 0 must be mapped in 0 prime, I denote it, and 1, the same, must be maps in 1 prime. And we have here results about a connection between morphism of order-generated hyperrings and multi-lattice morphism. Okay. And I gave some examples. Some words about future results. This theory is applied with success in physics, in artificial intelligence, hyper algebraic logic, multivaluate logic, support fuzzy reasoning, and knowledge representation. Also in social sciences, for modeling nonlinear aspects of behavior in networks and opinion dynamics, in machine learning, coding theory. And at the end, I wish to present some books. The first book about hyperstructure, written by Corsini. There was at the same period a book of hyperstructure written by Professor Vuciuclis about representations of hyperstructures. The book that I mentioned about applications, and together with Professor Davas, I wrote 3 books. One about hyperring theory and applications, the second one about hypergroup theory, and the last one about Krasner hyperring theory. The paper of Benado. Some colleagues from Spain worked on this topic on multi-lattices and their applications for non-deterministic aspects. They published in Journal of Logical Computation. And some other papers by the Greek school. And I have a paper with some colleagues from Africa, Nijnu, Nikpeya, about derivations in hyperlattices. Similar as Professor Vuciuclis presented the derivation yesterday. I thank you very much for your attention, and I finish my talk here.
Thank you, Violetta, for your interesting talk.
Thank you.
Any questions from audience, online and offline? Yeah. Right.
Thank you, Violetta, for the presentation. It's really very interesting, and your way in letting us understanding thing. It means that you're a great instructor in the class. So your students, for sure, they admire your ability to understand from you. I have just one. You gave an example, and I was writing it. I found it very interesting. It's when we start with H as hypergroup, G as abelian group, and you put the A index I with A1 equal H, and T is the union, and
Yes.
you introduce the hyper operation. You put the hyper operation as A square B equal A round B if both of them in H, and if
Yes,
both of them
I put
are
here
not,
the example.
yeah. But what if one of them, so if one of them is in H and one of them is in AI or AJ, what will be the hyper operation between them? So this one,
if both of them are in I, that you ask?
Yeah, if both of them are in H, you put the result, and
Okay.
if both of them are not in H, you put the result. But what if one of them is in H and the other is not in H?
I understand. but H is actually A1.
Oh, okay. So it will
So,
be the same. You will use it. Yeah, yeah, I got it. Okay, okay. So no need to write.
It was of Corsini example, this one.
Yeah, yeah,
At
yeah.
least I
got
found,
it.
okay, I found this example in his book. Maybe he took from some other paper, but just
But now it
one.
makes sense. Yeah, yeah, because I just so it's one of them is in H. Yeah. So
Okay.
it's thank you so much. Appreciate it.
My pleasure. And thank you.
May I speak?
Yeah, sure, sure.
May I have? Can I
Yes.
speak?
Yes, yes, please.
Yeah. Yes. And now for your presentation, it is very interesting for me because I saw this history. For example, I saw the names that you mentioned. For example, Mitas,
Yes.
and Corsini. Corsini started from a paper of Mitas from
Yes, I know.
canonical Hyperstructure groups. And
Yes.
then also I met Krasner, who was the first one where I present my PhD results. And later, all these people like Comer, Jatosak, and so on, you remind me a lot of those persons. And I like to say to the audience that Violetta, I know Violetta from the age when she was very young, and
30 years ago, 33 years ago.
3 years ago, yes. And Violetta and Davas were the invited in the eighth AHA
Yes.
conference. They were, I put them as the main speakers, and I left all the others to attend them in order to see how they choose hyperstructures in their interests. And I think it was my good choice
Yes, very
to.
good.
You remember, Violetta, it was in the island of Samothraki,
I
and the
remember.
conference was 9 days.
Yes,
So
I remember.
only few words, a few talks, and then we talk separately all these people.
Yes,
Thank you
thank you
very
very
much,
much.
because
Good remembering.
I think that it is my I I think that I discovered you.
Thank you
You
very
a
much.
good discover. Okay, thank
Thank
you
you
very
very
much.
much for all.
Hello, Violetta. There is one question from audience here.
Okay, thank you.
Okay. Be audible, you can from there also. You can talk loud. Hello.
Hello.
So I have a question that what you are calling as multilattice. Yes, no. That why is it not given the name that hyperlattice?
In a hyperlattice, the join and meet can have more elements, it's true, but these elements are.
But in multilattice, where is the difference? Here
the
also,
different-
when join, you have more than one element.
Yes, but here, instead of supremum, for instance, we have a set of minimal upper bounds. And in hyperlattice, we do not impose this to consider the set of minimal upper bounds. We have just a set of elements.
I see.
So the just a moment, because it is very intuitive, the diagram. A join B is a set CD. It cannot be any element. It cannot be 0, it cannot be 1. But if we consider a hyperlattice, they could be. They could be because it is not imposed that we talk about minimal or maximal
I see.
bound. Yes.
Oh, this is the difference. Okay.
Yes, this is a particular type of hyperlattice.
Oh, particular type of hyperlattice. You are giving, you are putting restrictions on hyperlattice.
Yes. But also in a hyperlattice, I think in the definitions there are restrictions. But I do not know if about minimal or maximal bounds.
I see. I could understand. Then, how is
Okay.
the theory developed? That how much is it developed compared to the classical lattice theory?
This is an old notion introduced in 1955 by Benado, but not in relation with hyperstructures. He considered it for the theoretical point of view. It is enough old, and it is a study for non-deterministic aspects. In application, colleagues of Spanish school, Cabrera, Cordero, Gutierrez, Martinez, and Ojeda Asiego, studies this in connections with computer science. So they are professor to computer science in Spain, in Malaga. Both of them, most of them. I don't know if everyone, but most of them in Malaga, in Spain, and they studied multilattices for computer science.
Oh, I see. Okay. Thank you. Thank you for the information.
My pleasure.
Thank you.
Okay.
One more question is there. Hello.
Hello.
So I have two questions. So first one is there any characterization of heighting algebras via your joint spaces?
Heighting algebras, no.
Oh, okay.
It
And
could
then
be a new research topic.
Okay. Thank you. And the next question may be a silly one. So if you fix a set, so is there any way to build a non-trivial hypergroup freely from that set?
A non-trivial hypergroup from a set. For instance, using the definition of Vujuclis, if we consider P a subset of H, we consider X times Y equal XP Y in a group. So we start with a group. P, a subset, P, a subset of a group, and XY is equal XPY. Or we can consider more intuitive the closed intervals if we consider the real set between X and Y. X times Y is the closed interval between X and Y. If we have the real set. But if not, we can consider as a non-trivial hyperstructure the construction of Corsini. We take the element Z between the minimum and the maximum. The book of Corsini starts with a list of hypergroups of examples, many hypergroups that can be considered also in connection with relations. But also that ones that I give about connection with lattices, they are not trivial.
Thank you.
Okay.
May I notice something on this question?
Yes, you can. Sure.
You see, this p hyper operation was the example that when I heard about the definition of hypergroup, I didn't know anything about this topic. I speak about 70s, okay? And it was a very good example to produce a lot of hyper operations in the classical way, not weak ones. So this P hyper operation can be transferred in every classes of structures to produce hyperstructures. For example, this was done by Serafimido using P hyper operations for lattices and so on. And another thing is that about the definition, you see, we were in the beginning of this theory, so maybe we have we did not decide about the names hyper, multi, hypercompositional, and so on. So we had in the beginning different names, but now I think that hyper is most influenced. Okay.
Thank you.
Hello, Violeta. There is a question from Aishwarya. She want to ask one question.
Yes.
POSET which is not a multi-lattice.
POSET is not a multi-lattice, but in a POSET we have only a order. Only a order. But for a multi-lattice, we must have minimal and maximal elements for upper bounds, lower bounds. We can use Zorn lemma. Zorn lemma assures us about the existence of maximal elements. So in a POSET, if we have the Zorn lemma, we can obtain maximal elements, for instance, and dually minimal elements. So not only a POSET, but a POSET in which Zorn lemma can be applied.
POSET doesn't satisfy Zorn's lemma. It cannot be a multi-lattice.
I don't understand.
Her question is the POSET which doesn't hold the Zorn's lemma cannot be a multilattice.
I think no. Only in the finite context we can. I present here the finite context in order to have this element, the minimal, maximal. But if it is not finite and we have not Zorn lemma, no, we cannot have maximal and minimal elements. This is an important tool, the Zorn lemma, in order to have maximal elements.
Okay, thank you. So with this one, I would like to thank Violeta for your nice presentation and the question answer session. So next we will move on to the next section. We hope that Sabha is online.
Yes, good morning.
Good morning, Sabha. I'm Harishran here.
Hi.
How are you?
Okay.
I have to stop share. Okay.
Yes. I think Irina is also online.
Yes,
good morning.
Good morning, Irina.
Okay. Should I start, Harkishan?
Yes, you can.
Okay, good morning, everyone. And really, it's my pleasure to be with you today. And really, also my pleasure to introduce our next speaker, Professor Irina Cristea. So our professor for today, Irina Cristea, received her PhD degree in mathematics from the University of FDS of Constantinia, Romania. She concluded her postdoctoral studies at the University of Udine, Italy. She currently works as an associate professor at the University of Nova Craiova, Slovenia, where she leads the Center of Information Technology and Applied Mathematics. Her research interests are mainly related to the theory of hypercombinations algebra, having published more than 80 articles in journal indexes by Scopus or the Web Science, and co-authors one book entitled Fuzzy Algebraic Hyperstructures, An Introduction, published by Springer in 2015, Over the past 5 years, she acts as the chief editor for Italian Journal of Pure and Applied Mathematics. Currently, she acts as an associate editor for she's an associate professor or editor for mathematics published by MDBI, Helion Mathematics published by Sil Press, Open Mathematics published by Diekers and Brill, and other international journals. She's also a guest editor for several special issues related to algebraic structures and the graph theory, and she actively participates in differential national and international projects. Please welcome Professor Irina Cristia, please, with me. Stage is yours, please.
Thank you very much for this nice presentation. Thank you very much for the invitation. I'm happy to be here and meet some of you. I didn't know Saba, so it's the first time when...
Yeah, it's me, Rosa. It's my pleasure to meet you, really, today.
First of all, I didn't know that you are a woman, so I always consider you a man, and this is my mistake, you know. This is the problem.
Change it, please.
Yeah, with the names, we always have these problems when we are coming from different
countries. Yes, yeah.
I will try to share my screen. Can you see it? I will make it full mode, full screen mode.
Yes.
I lost it. Just a moment, please. Yeah, can you see the presentation?
Yes, Irina.
Okay. Thank you very much. Yeah, as Saba mentioned, so I'm originally from Romania. I live in Italy, in Udine, where I concluded my postdoctoral studies. And after 8 years of the University of Udine, I moved in Slovenia just with the work. So I'm currently at the University of Nova Gorica in Slovenia, a very small university, unfortunately without a faculty of mathematics. But we are struggling to continue to develop the theory of hypercompositional structures. And for today, I choose one topic. It's not a new one, about HX structures. These are classical structures, so we don't have a hypercomposition on them. But they were studied for several years by also by Professor Corsini in order to connect them with hypercompositional structures. So here I will present some preliminary results. I may say that there are a lot of open problems. So this could be one of the next topics that we will hear about in the other conferences. Some words about the history and the terminology, because unfortunately also here there are a lot of confusions. And then I will focus on HX groups, talking about presenting some types of HX groups, some constructions, and an attempt to define HX polygroups. Then the other notion is about HX rings and power rings. These are two different structures. I can say that nothing till now appeared on HX modules or HX fields, but I can tell you that immediately you can recognize that they can be defined very easily. So we know already after so many presentations yesterday and today, what is a hypergroup is the one that was introduced by Martin in 34. Then between 33 and 39, a group of Americans, so Orr, Drescher, and Eaton, defined multi-groups. Yeah? So not hyper, but multi. as the group-like system with non-unique multiplication that are in fact equal with Marty's hypergroup. So this idea was abandoned and their papers were not, and I think they are also not cited, but really very interesting to read them. They can be also found online. In 1973, Dunkel defined the hypergroups that are currently used in harmonic analysis, and we know that nowadays we have to pay attention on the publications that appear on hypergroups because they are practically in two different fields, so our algebraic hypergroups and those used in harmonic analysis. In 1985, a group of three Chinese mathematicians defined hypergroup, so again the same term was used, hypergroup, as an upgrade structure of a group. But later on, in 1987, since they discovered the Marty's, or not just the Marty's, but the other publications on Marty's hypergroup, they changed the name and they called them HX group. And pay attention that this, let's say, term is connected with the initial letters of his name. So Hong Xing, that's why he defined HX groups. And the definition appears in the next frame. Recently, in 2003, another hypergroup was defined as a linear as a spatial complex unital associative algebra. So we have different mathematical structures having the same name. What is a HX group? So we start with the group, a classical group, where the neutral element is denoted by E, so neutral element or identity is the same. And on the set of the non-empty subsets of G, we will define this binary operation. So it has some similarities with the hyper operation, but this is really a classical operation. A non-empty subset of the P star of G is called an HX group if with the operation defined before, it is a group with the neutral element denoted by capital A. So the small e is for the initial group G and the capital E is for the HX group. A simple example. We start with the direct product between Z2 and Z3. The neutral element is the element 0, 0. I consider two sets B1 and B2, and then we can obtain this following HX group with the neutral element E being equal with the set B1. Sorry. The neutral element, the inverse of any element in the group, in the initial group, is denoted by G-1. But here we have also the inverse of any element of the HX group and is denoted with A-1. Pay attention that we can also consider the set of the inverses in the group G, and this is called the inverse set of the set A. And then we can construct another set called G star is the union of the subsets of the elements in the HX group G. Then we have two types of, immediately we can distinguish between two types of HX groups. The ones called uniform HX groups, where the inverse of any element in the HX group is equal with the set of inverses in the group contained in A. And it is regular if the identity of the neutral element of the initial group G belongs to the neutral element of the HX group. As an example, if I consider the group of the positive real numbers with the multiplication, then for any positive rational number A, we can consider the semi-closed interval A infinity. Then we construct the set G round and italic G, let's say. And we can notice that this is a regular HX groups on the initial group G, with the neutral element being the interval 1 to infinity. So here we can notice that E minus 1, so the inverse set of E, is equal with E, while the inverse, the set containing the inverses in G is 0, 1. Yeah, so these two sets are not equal, so the HX group is not uniform. For an HX group G with the neutral element E, we have these following properties. It's interesting to see that the inverse set is a subgroup of G. Also, the neutral element of the HX group is a subgroup of G. And another important property is the this one where G star, I remember, is the union of the sets of G, is a subgroup of G, and for any two elements such that A is included in B, it follows that they are equal. So all these properties will be used in the next part, where I will show you how to construct HX groups as quotient structures. This is the only construction that appeared in the literature, so maybe we can think to obtain them also in another manner. Let H, the first proposition says that let H is a subgroup of an arbitrary group G, and an idempotent set, so E times E is again E. If for any element in the subgroup, the property AE is equal with the EA holds, then the set G rond is an HX group of the neutral element E. Moreover, if E is a normal subgroup of G, in general it's just a subgroup, but if it is a normal subgroup of G, then this HX group is regular and uniform. Indeed, the surjection F defined from the subgroup H to the HX group G, in the intuitive manner, f of A is the class AE, is a group homomorphism. So this means that I can quotient H with the kernel of this surjection, and the quotient set is isomorphic with the HX group G. This set is called the left quasi coset of E, while the other one clearly is the right quasi coset. The second proposition says that if I start with an HX group, the following assertions are equivalent. So this is a characterization of the regular HX groups. If for any element in the HX group, there exists another element A in the set capital A, such that this set is equal with the left quasi-coset of E and right quasi-coset of E, we characterize the regular HX group G. As an example, no, sorry, okay. I tried to, and I think this was 2 years ago, to construct to extend, let's say, this construction to the case of hypergroups. And since there is a big correspondence between groups and polygroups, first we wanted to define HX polygroups. I say that this is a tentative study because it was not concluded. We left the article with some open problems. Still, we are working on them, but we couldn't find the answers. So if P is a polygroup, and then H is an HX subset of P, We say so HX subset, it's a set with the property that for any two elements A, B, there exists another one such that the intersection between C and the product, the composition between A and B is non-empty. We say that H is an HX polygroup on the polygroup P if H is a polygroup, so as we know from the hypercompositional algebra, with the hyperoperations defined in this way. So I will take two elements and consider the set of elements C with the property that the intersection between C and the binary operation AB is non-empty. As an example, how can we obtain this? Let's start with a polygroup with the scalar identity E, and N be a normal subpolygroup of P. Then we can construct the quotient polygroup, and we obtain that this is indeed an HX polygroup based on our definition, where the hyperoperation is defined as we can see here in the slide. Another example is this example was inspired by the Comer paper when he defined the coset of polygroups. So if H is a subgroup of an arbitrary group G, the system of all double cosets, yeah, so this is denoted GH, is HXH, where X is an element in G, is a polygroup. Then we can define another operation. In this case, it's an hyperoperation because it's the set of all elements having this form. And we concluded that the set G is an HX polygroup on the initial group G, called the coset HX polygroup. Now, what are the questions that arise? We know that every HX group constructed on a finite group is regular. It can be seen as a group of cosets. But what can I say about polygroups? Is every HX polygroup that is constructed on a finite polygroup a polygroup of cosets? And the answer was no, unfortunately, as the following example shows. So we consider the set P with 4 elements with the hyperoperation defined in the first table, is a polygroup with the scalar identity E. Now considering the set of H of the two subsets, we obtain that it is an HX polygroup. And moreover, since the product between the set containing E and A and X is different by the set BC for all X in P, this shows that H is not a polygroup of cosets. But what was nice that it is a double coset HX polygroup. So if we calculate HEH, HAH, we obtain that it is the set H containing E and A. And again, HBH and HCH is the set containing B and C. So this was a nice example contradicting let's say, the general result, but showing how we can obtain a double coset HX polygroup. Another example, considering the group, the cycle group of order 3, so with the elements 0, 1, 2, then we considered P to be the set containing the subsets 0 and 1, 2. Then we define the hyperoperation based on the Cayley table. And this is again an HX polygroup on G, which is not a polygroup of coset nor a double coset of HX polygroups. So we can see that we couldn't obtain any relationship between the polygroup of cosets and double coset of HX polygroups. So still we can work on this with this aspect. And that's why we raise this question: when can be an HX polygroups seen as a polygroup of cosets? And the first theorem that we obtain says that if we start with polygroup P and then H to be an HX polygroup on P with the identity E, satisfying these four conditions, unfortunately, here we have four conditions that have to be satisfied, then H is a polygroup of cosets. But when can be an HX polygroup seen as a double coset of polygroup? And also here we obtain a nice result, starting with the group G and an HX polygroup on G with the scalar identity E. Then we take K, the union of all elements in the HX polygroup. If this is a subgroup of G, then the HX polygroup is a double coset HX polygroups if and only if we have this supplementary condition saying that EXE is an element in H for each X in K. This was the first part regarding HX groups. These structures were studied more and also recently, so 10 years ago, but also nowadays there are several publications on HX groups. What was less investigated and was investigated more just by the Chinese school is the other structure called HX ring. Very interesting is that HX rings were defined by the same group of researchers 1 year after the definition of the HX groups. And here we start so we have to define two operations, and it's a classical definition of a ring. We denote by Q the zero element of R, and also we have to pay attention to how the opposite is defined. Yeah, so this Q element is a set, and it is not necessarily the one containing the zero element of the initial ring R. While by minus A, we define the opposite element of A. So minus A plus A is equal with Q. An HX ring is said to be regular if the zero element in the initial ring belongs to the zero element of the HX ring. As an example, so this is I would say a trivial example. If S is a subring of a ring R, then the set containing just singletons is an HX ring on R. If A is a non-empty subset of R such that A plus A is A times A is equal with A, so it's idempotent here, it's a mistake, then the set containing just the element A is also an HX ring, and these are trivial examples of HX rings. Let's see a more complex one. So we start with the ring R being the direct product Z times Z, and then the HX ring R is the set of non-empty subsets of the direct product between Z and 0. Yeah, so it contains the elements of the set of the elements of the form A0, these pairs. Both addition and multiplication are closed operation, but the other axioms of a ring are not verified. And this was one source of mistake in one publication that I found. So 0, 0, the pair 0, 0 is a good candidate for being a zero element. But for example, if I take the element A containing the pairs 1, 0 and 2, 0, in order to find its opposite, yeah, I need to find another element, let's say B, such that A plus B is 0, 0. But this means that in order to get 0, 0, I have to consider to take B to contain -1 and 0 and -2 and 0. But then when I do the sum, what I will obtain, 1, 0 plus -1, 0 is 0, 0. But then I have also to make the sum between 1, 0 and -2, 0. And I will get -1, 0. And 2, 0 with -1, 0, I will get 1, 0. So we can see immediately that this is different by the set containing just the neutral element 0, 0. Yeah, so B cannot be the opposite of A. And this was not a good example of an HX ring. Because it is not a group, so also we cannot define the ring structure. But in order to overcome this problem, we will take R to be the set of all singletons of the same set P star of Z times 0. So make the difference between, we have to pay attention on how is construct now the set R, yeah, is the set containing the singletons. So singletons are set with one element, and this one element is A0. In this case, indeed, 0, 0 remains the zero element, and the opposite of any element A is the one containing just the pair minus A and 0. And this is a nice example of an HX ring, which is isomorphic with Z, yeah, because we have 0 here. This is another example, a more complex one, where the properties of the natural logarithms were used in order to fulfill all the conditions of a ring structure. So the sum of two elements, of positive real elements, is their classical product, while the multiplication is defined of the module of A to the power of the logarithm of the absolute value of B. This is a commutative group with the addition. The associativity is satisfied based on the properties of the logarithm. So very nicely, the associativity can be checked. And this means that R star with the multiplication is a semigroup. Also, the distributivity holds. So really, this was a nice example of an HX ring that was constructed starting from the positive real numbers. If H is just the set containing the elements -1 and 1, this is a subring of R star, and then I is the open interval from 1 to plus infinity. The set I satisfies these equalities that were required in the previous proposition. And then if we consider, notice that also here we have to take the elements as like a construction of a quotient. So similarly as in the case of HX groups. So if R is the set of the elements A plus I plus the interval I, we obtain is the union between the two intervals. The first one I denoted by A1, and the second one is the interval I that was considered before. Then this is an HX ring with the zero element I, but it is not a regular because the identity, the zero element with respect to the addition of R plus was 1, and this is not contained in our zero element here, yeah, because we consider the open interval from 1 to plus infinity. And we have, as in the cases of HX groups, we have also here several types of HX rings. The normal ones are those when the set of the zero element with the addition is a monoid of the initial set R with the identity, and uniform if it is a subgroup of the R with the addition. The example that I showed you before is neither normal or uniform HX ring on R star. But it was constructed as a quotient ring, yeah? In general, the multiplication of a quotient ring is not coincident with the HX multiplication. In fact, if I is an ideal of a ring R, then for any two elements R1 and R2 in the ring, we have the inclusion and not the equality. That's why this was the motivation example, if I can call it like this, for defining a new class of a new structure called, again by the same group of Chinese mathematicians, power ring. Both are defined on the same set P star of R, where R is a classical ring, and here the HX operations were a little bit different. The addition remains the same, so A plus B is the set of the elements A plus B. But the multiplication is the set containing the multiplication of the two elements A and B. And if R with the new two operations form rings, then it is called a powering on the initial ring R. If the zero element is a subring of R, then R is a uniform power ring. What is the relationship between these two structures? All HX rings are also power rings, and all quotient rings of every subring are power rings on R. Yeah. So these are again called trivial power rings, and they were not considered in the other studies. But I would like to introduce some examples. So you see here I define, I start with the real ring, the ring of real numbers, and E is the open interval from 0 to plus infinity. Then we can construct this set R, defining the two operations in the classical way. This is a ring, but it is not a power ring, because if I make the multiplication between these two elements, what I will obtain, -1 times 2 is -2 plus E. While if I do the multiplication between them, so it's not included in the set -2 plus E, because the element -1/3 is in the first set, times 9 is in the second set, gives me -3, which is not included in the interval -2 plus infinity. Yeah, so it's not all HX rings are power rings, but they are different structures. Again, how can we obtain these HX rings? There are several theorems, all of them more or less similar. So if H is a subring of a ring R and E a non-empty subset of R such that I plus I is I, so it's an idempotent. And then if I define the multiplication in the classical way, then I would say the quotient set is an HX ring on R with the 0 element I. An example taken from the matrices. This is very clear example. So on the set of matrices 2 by 2 with integers, let's consider H the one having the last line equal with zeros. E the set with the matrices having the first column equal with 0. H is a subring and I plus I is equal with I, so it's an idempotent. And now if I consider two elements and I will calculate H1 plus I times H2 plus I will get that it is indeed H1, H2 plus I. Based on the previous theorem, the new set is an HX ring. The 0 element is the one contained in I, so it is a regular HX set. Besides, since I is a monoid of this ring, but not a subgroup, it follows that the quotient is a normal HX ring, but not an uniform HX ring on R. And in order to get uniform HX rings, we have to start with a semi-ideal with respect to the subring H. So here is not a semi-ideal in the ring R, but is a semi-ideal with respect to a subring H, meaning that the property in the bracket must be satisfied. Again, if I is an idempotent, then this relation is satisfied. So practically, in order to define these HX rings, we need the equality to be satisfied. And the question was for which kind of subsets I, this identity was satisfied. And one of them is to consider it as a semi-ideal with respect to the subring H. Here I showed how the property is satisfied. The second construction starts from a subring. Again, I is a non-empty subset of R such that it's an idempotent with respect to both operations. And if we have these supplementary conditions, so the multiplication between A and H on the left and right side is 0, then again we obtain an HX ring on R. Here it's an example, again from the matrices 2 by 2, satisfying the previous theorem. The other notion that was useful was the one of regular semi-ideal with respect to a subring H. So you see here the definition, and this was again used in order that the condition was fulfilled. What is important to notice is that the power ring H quotient I is not a quotient ring. So it is a power ring because there is not this inclusion between the sets I and H. Yeah, so there is no relationship between these two. Again, an example on the set of matrices 2 by 2. And this is an example of a power ring, but not of an HX ring. So these two structures are not are distinct structures. And this is the last theorems where the notion of semi-ideal with respect to a subring was defined. And here the 0 element has an important role in this theorem. And the example that I found related with this theorem was on the set of matrices 3 by 3, so with a lot of zeros here just to simplify the multiplication. And again, this is a non-regular power ring, but not an HX ring. I don't remember exactly when I have to finish. I think now, right? I'm running out of time.
Like 2 minutes.
2 minutes. Okay, 2 minutes just to just to show you a little bit of the references. So you can see the initial paper in 85 was published in Busfall. Unfortunately, it's not easy to get them, but who is interested can contact me, and I managed to have not all of them, but some of them. You see that also Corsini worked on these HX groups and hypergroups, because he constructed hypergroups starting from HX groups. And also Andromeda Sonia worked on HX groups associated with the Edler group. So there are several papers on HX groups, but very, very little on HX rings and power rings. That's why I think that this could be a good topic for further research. Thank you very much for your attention. If you have questions, I'm pleased to answer.
Thank you, Irina. And really, I'm excited and interesting topic. And if anybody has a question, please. So should I start? If it's okay?
Yes, please.
Okay. So since HX ring and power rings are closely related, so what do you think, under what necessary and sufficient conditions does an HX ring become a power ring?
I can't answer you, unfortunately. We found just several examples when they are equal, but a general rule till now we couldn't discover.
Yeah, since we think they are related, there's some requirements or conditions should be like relate both of them.
I can't answer you now. So we just know that HX rings are power rings, but vice versa, when they are equal. Yeah,
not yet. Okay, thank you.
Could be for a fact for a future article.
Yeah, maybe. Thank you. Any other questions, please? Any other questions? Harkishan?
Yes, there is one question from.
There's one question, Irina, please.
So I could not follow one thing that in one of your slides you have written that -1 is a subring of R star.
-1 is?
-1 and 1, this set, the set consisting of -1 and 1 is a subring of R star.
Yes.
You have written...
Wait. Here.
Yeah, this one. R star means the R -0, right?
Yes.
So R -0. All right. So subring, that means here what about the plus operation?
Wait, so you have to consider these two operations, yeah? So
I missed this point. I missed.
So it's connected with the same. I have to insert it into different frames, slides. No.
Got it. I missed this definition. Right?
Yes, so this is a very complex. I think that the authors really did an excellent job verifying all the properties. So it's not the R star with the addition and multiplication, classical addition and multiplications, but here the operations were changed.
Yes. Okay, now it's okay. Fine. Thank you.
Thank you. Yeah. Also, the presentation, we don't have enough space on the slides to put everything together.
There is one more question, please.
Please.
Hello.
Yes. Hello.
Yeah. So, is there any Grothendieck style group completion of HX monoids towards HX groups?
I'm not sure if I correctly understood the question. If there is some work on HX monoids,
No. Is there any
No.
Grothendieck style group completion of HX monoids?
HX monoids.
HX monoids were not studied till now, so I couldn't find any. I think there is nothing worked on this topic.
Okay, thank
So
you.
this is again an open problem.
Thank you.
Okay.
Sabha, you can proceed with the conclusion.
Okay, thank you, Rina. And we wish to work more and more together. And so what is next up, please, Harkishan?
The next talk is by Sarka. You can thank the speaker and hand over the session to the.
Thank you, Rina. Thank you.
Thank you very much. Just a moment because I have to stop share.
I think Mediline is available online to chair the session.
Yeah, I'm here. Okay, let me just check. Yeah, I'm not muted. Okay, shall we start?
Yes, you can.
It's a real pleasure to introduce our next speaker, Professor Sarka Huskova-Mayurova. I have had the privilege of collaborating with her on several research projects over the years, and I have always admired her enthusiasm, professionalism, and dedication, especially to fostering international collaboration. She's a professor in the Department of Mathematics and Physics at the University of Defense and has held several academic leadership positions, including serving as Vice Dean for Public Relations and Development. Her research spans interdisciplinary subjects, including mathematics, military sciences, crisis management, and math education. And she has led and contributed to numerous national and international research projects. She's the author and co-author for more than 120 scientific publications, including over 80 journal papers, and has organized many international and national conferences as executive director or chair of the program committee. Beyond her impressive publication record, she's known for bringing together researchers from diverse disciplines and creating opportunities for meaningful scientific collaboration and, as a result, interdisciplinary research. Today, she will present Hyperstructures and Fuzzy Systems in the work of Antonio Matoro. I'm not sure if I'm pronouncing his name correctly, from Algebraic Foundation to decision-making applications. We will learn about his journey on hyperstructures, fuzzy systems, and their interdisciplinary applications. Knowing Sarka, I'm sure she will not only present his journey, but also she will convey the broader impact of his work on our research community. Please join me in warmly welcoming Professor Sarka. Sarka, the floor is yours. You can share your screen.
Sarka, you have to unmute it.
Press on the audio part.
Unmute. Now maybe you hear me? Oh, perfect.
Yeah, we're hearing you.
Good afternoon or good morning for everybody. I am very happy that I am now with you, and I am very, very sorry about my mistake yesterday. We have a semester, we have a term, and I have an exams, so I mixed the time, and I was not ready. I was in another meeting, so very, very sorry. I would like to try to share my screen, if you will be so kind and help me. Do I share? Do you see my presentation?
Not yet. You need to press on
Not
the
yet.
share. Yeah.
Do you
There
do you
is
see
an arrow. No. There is an
No?
arrow between more and react. So press on it, but you need to open your presentation before.
Tak, I open my presentation.
And press on share.
Od začátku. And where to press to share now? If it's on the full screen.
There is an arrow, or you can press on Alt S. If you want to use your keyboard, you can press on Alt S, or
Alt
it's
S?
between, yeah.
Okay, I will
and
try.
then choose the window that you want.
Start. And Alt and letter S.
Yes,
Do you see?
like target. No.
You see my presentation or not?
No. Is it open on your computer?
Yeah, it is. I see it on my computer.
So there is something in front on the screen. There is something written share between more and react.
If I open the presentation, I don't see the Zoom, so I don't know how to
go
do
to
it.
Zoom. Then go to Zoom again.
I am on Zoom. I go to share.
Yes.
Now I see you, but how now? And maybe like
now
that.
Open the presentation.
It's
now
open.
You are sharing the whole screen, your whole screen. So open the presentation, we will be able to see it.
And now you see?
Yeah, we're seeing your whole screen. So you need to open your presentation.
I have it open, so I don't know what to do more. Sorry.
Okay, there is another option. You can stop share and just share, not the whole screen, share a window, share only the presentation. So press on share again.
Share, I press. No, I see you.
Okay, so now share. Press on share again and choose just your presentation to share. So when you press on share, you will see entire screen and the application windows. Choose only one of them. Choose the presentation only.
Share, but I see only you, the whole room in the India.
Oh, okay. Okay, do you mind sending me your presentation and you're muted, and I will share it from my end?
Or if you press Alt and Tab, I think you will get to the presentation. Can you press Alt and Tab? Alt Tab.
Something very wrong.
No, you can share your screen and then press Alt and Tab on your keyboard to get to the presentation. Share your screen as before, as you did before. Alt S to share the screen.
I sent by email, Madeleine, to you my presentation.
You
maybe you have
me?
it.
Okay. Yeah,
maybe if you can be so kind, it's
sure.
Email, and if
I
you
haven't
can
received it yet. Yeah.
And we will manage somehow because my computer is not cooperate with me.
I haven't received it yet, so let me just
maybe we need some time. Open. Menší od začátku. Tím si ztratím.
Yeah, now I receive it. Let me just I will share my screen. That weird.
It's possible.
I'm sharing. Let me just check. Okay. So let me just put slideshow. You're able to see the screen, right?
Yeah, I see.
Okay. I will make it slideshow mode. Let me just check. Okay.
Okay, we can start here. So thank you very much for your help, and I hope now you see my presentation. I am very happy that I have the opportunity to attend AHA conference again after a long time. This conference meant a lot in my professional life, because as a beginning, as a doctoral student, I learned about this conference from my supervisor, from Professor Chvalina, who was at the time very involved in hyperstructures. And thanks to the kindness of Professor Thomas Vojoukris, I had the opportunity to come to a beautiful island, Samothraki, in 2002, and met a wonderful group of people who were dedicated to study hyperoperation, hyperstructures, and their properties. Here I gave my first lecture in my professional life in English, first lecture abroad. I was at the time really very stressed, but Thomas helped me a lot. He calmed me down, and I was able to stand in front of the full hall, packed of the experts, and to pronounce my lecture. And from that time, I was determined to hyperstructures, and my professional life was orientated to this topic of algebra. In Samothraki, I also met Professor Antonio Maturo for the first time. He gave a lecture on a topic probability, utility, and hyperstructures. And over time, a strong bond of friendship and a long-term cooperation developed between two of us. Those who knew Antonio know he was a very nice, sociable person, but his spoken English was indeed very Italian. Antonio claimed that I was the only person who was able to understand his spoken English. In early April of this year, unfortunately, Antonio died. So I decided to give this lecture into his memoriam and to dedicate it to him, to his personality, and to his work. Thank you very much. I would like to start my lecture with introduction of his academic career, because this is important for the beginning. The development of mathematical tools capable for representing uncertainty has become one of the major challenges of contemporary science. And Antonio, he started from this part, he started from probability at his beginning. Classical algebraic structures and binary logical frameworks often prove insufficient when dealing with complex systems characterized by incomplete information, multiply outcomes, and subjective evaluation. Among these approaches developed to address this limitation, algebraic hyperstructures and fuzzy sets theory occupy a prominent position. And Professor Antonio Maturo developed a substantial part of his scientific career to exploring these two domains and, what is more important, to investigate their intersections and interactions, of course. Working for many years at the University degli Studi in Pescara, Chieti. In fact, sometimes it was in Pescara, sometimes in Chieti, as these are two cities very close in Italy. He contributed to research and teaching in mathematics, economics, and mainly social sciences and decision theory. Through numerous international collaborations, conference activities, and editorial work, he helped to disseminate hyperstructures theory and promote its application beyond pure mathematics. Antonio participated in many conferences, and he do a lot in editorial activities. The most important, in my opinion, was that he was editor-in-chief for many years of Ratio Mathematica. I found here one cover of Ratio Mathematica, where not Antonio, but his son Fabrizio is editor-in-chief, but I think 20 years before Antonio done this job. And also he participated in many editorial activities of various collective monographs. In addition of his teaching and research activities, he was also very active in international scene. He collaborated using Erasmus in various European or mainly European universities, not only European because he liked traveling. So he was in various parts of the world, and his wife Angelica accompanied his to these trips. He participated in various scientific projects and conferences, and I would like to mention one for our point of view main important, and it was a conference AHA in 2011, which he organized for us in Chieti, and we enjoyed the time not only via Mathematica, but also via dancing, which he loves a lot. We can continue, please. Next slide. I would like to show how his professional life started. His first publication was done, or I found like the first publication in 1983. And in this year, he published 3 publications for the main, and 2 of them were books. What was quite surprising for me to starting with the book. The professional career is very extraordinary. And on the other hand, on the next slide, I prepared the last publications of his life. So, Madeline, please. Thank you. These are his last papers published with colleagues, with Luciana Rocchiri and with Renata Santarossa. And as you can see, he changed the language. He started in Italian. Now the papers all are in English, and the topics are fuzzy and decision-making problems. Some words about his bibliometric overview. I check at ResearchGate, and you can see that he was really very active, and I am sure that conference papers were not only 12, but many more. But on the ResearchGate, you can find these 12 for maybe the highest or biggest conferences around the world. His friends and authors were people which I mentioned at this slide. The majority of paper which he had with co-author were done with or were done together with Aldo Ventre, our colleague and friend from Italy, from University of Campania. He also published a lot with architect from Pescara, with Professor Barbara Ferri, and he published quite a lot with Luciana delle Rocchiri, a teacher from Pescara. Here they published possibilities how to use hyperstructures in decision-making process in social sciences, problems with decision, and using in or application on children or various examples from life in the elementary schools. Not only these, also Rina Manuela Contini and I was his co-authors. Thank you. We can continue. Now I would like to postpone or to not postpone to go on his early research and say several words about his starting points, how he was inspired to the probability theory logic, and starting from classical algebraic theory to algebraic hyperstructures. He was inspired by the coherent probability framework of mainly Bruno De Finetti, and he investigated the algebraic representation of conditional events. The conditional events were the starting point from Antonio, and associated uncertainty with these events, and from this he defined hyper operations, and then he continued with studies of probability from studies with not probability, sorry, I missed the word, with properties of these conditions. Okay, we can continue to another slide. One of his most influential early contributions was introduction of hyperstructures associated with conditional events, as I mentioned before. Together with Serena Doria, he proposed hyperstructure models capable of representing situations in which the composition of events does not lead to a single outcome, but rather to a set of possible outcomes. Such multivalued operations naturally fit to the concept which was introduced by Marty. We can continue. Their work, I mean work of Serena Doria and Antonio on conditional events for artificial intelligence demonstrated how hyperoperations could model incomplete knowledge and non-deterministic reasoning process. This represented an important step towards extending algebraic method into domains characterized by uncertainty and partial information. Subsequent studies investigated generalized probabilities, coherent conditional previsions, geometric hyperstructures, and hypergroupoids. Geometric motivation was very topical for Antonio, and hyperstructures associated with event spaces. These contributions establish a rigorous mathematical framework linking to probability assessment with hyperstructures theory. Now we can continue. A recurring theme throughout Maturo's research was the treatment of uncertainty, as I mentioned before. And regardless, hyperstructures not merely as abstract algebraic objects, but as powerful mathematical tool for representing the situation. His studies, generalized probabilities, and hypergroupoids demonstrated on various examples from real life that hypergroupoids provide a natural representation of uncertainty arising from incomplete information, as incomplete information is in social science very often, or it arises very often from the real life. As I mentioned, geometric interpretation was very topical for Antonio, and the interpretation of hypergroups is geometric, particularly joint spaces, and hypergroupoids connected with coherent probability was investigated in various of his papers and studies. We can skip this slide. Yeah, and we can proceed to the fuzzy sets theory and how his works were connected with fuzzy classification, fuzzy numbers, and fuzzy operations. This was done mainly with Barbara Ferry, Anna Maria Poreka and Professor Johan Tofan, where or together they developed models in which fuzzy classification generate hyperstructures and generate hypergroups associated with evaluation processes. They wrote a monograph which were written in Italy, Hyperstructure, Structure Fuzzy and Applicazioni, which means hyperstructures, fuzzy structury a jejich aplikace, represented, and this book represented a significant milestone in the direction of fuzzy set theory for Antonio and offer a systematic presentation of the interplay between hyperstructures and the fuzzy study or fuzzy methodologies. We can continue, please. I would like to mention that one most important aspect of Antonio Maturo scientific legacy was application mainly to decision making. Traditional decision models often assume precise preferences, as you know, definitely, and deterministic outcome. However, many practical situations involve ambiguity, incomplete information, and conflicting objectives and subjective judgments. Subjective judgments are very often involved, and it's not so easy to model them. And Maturo proposed mathematical frameworks capable of addressing these complexities. Can continue.
Not working for
One
me.
more, please. Is there?
Yeah.
Yeah, thank you. Here I mentioned, or here I prepare what was the main contribution in Antonio work. It was fuzzy evaluation of models for urban project, as he cooperated with a colleague who was, or she is still architecture, multi-criteria decision-making approaches in various part of social life, consensus formation method, aggregation procedures for group decisions, applications of analytic hierarchy and network processes, and mainly decision support system for social economic contents. As Antonio cooperated from people from various parts, he usually prepare or try to prepare paper or some examples from particular problem connecting with co-authors. And it was very nice to Antonio that he was able to find the problem which can be studied and to help people to proceed in this in their direction and to help them to publish what they exactly need for particular problems and for particular orientation of the person. Yeah, we can skip this. And we can stop here. I would like to mention something or some words about his latest works. And during his latest studies, he was focused on multi-agent system in social sciences. So he published and he studied multi-agent decision making, consensus building among decision makers, fuzzy logic and fuzzy set theory, of course, mainly modeling in economics and social sciences, and group decision making and preference aggregation. Aggregation was also very important in Antonio works, and it was linked during his all professional life. Here I have some key publications concerning this social science and multi-agent systems. We can continue. Yeah, and what to say about this work? His research address mainly these questions that I try to formulate it. How can the preference of a multiple actor be aggregated? How can consensus be achieved? How can social conflict and cooperation be modeled? This social conflict and cooperation were with Luciana very often because she worked in elementary school, and the conflicts between small kids were often involved. Various type. I don't think only a serious one. I think various type of conflicts, and they try to model and they try to find the way from such a situation. And the last important question which was in his mind was, how can fuzzy logic support group decision-making process? So I can say that Antonio has the place among the scholars who bridge decision sciences, social sciences, and multi-agent decision system, providing mathematical frameworks for understanding and supporting collective decision-making in complex social environments. This is the conclusion, and I would like to say that I am very sad, and his work leaves a lasting mark and inspires, I hope that inspires not only me, but future generation of researchers to take an interdisciplinary view of society. Interdisciplinary view was really a link which follow Antonio during all his professional life. Honor to his memory. If you can show another slide, please, Madeline. Yeah, this is how I will always memory Antonio, or remember the Antonio, because he was cheerful and all the time accompany with the friends and with his loving wife, Angelica. I think I have one more or maybe two more photos. Yeah, here is Aldo Ventre, Antonio, and me. And the last, there you can see one more, please. Yeah, you can see here Irina, Violetta, again Aldo, Antonio, and Pier Giulio Corsini in this picture. So thank you very much for the attention, and thank you again very much for the chance to join you and to see you.
This is really a nice picture.
Thank you.
Nice remember. Yes, thank you very much.
Thank you.
Thank you very much, Sarka, for this inspiring presentation. And it really touched me that when someone that is working in the group, when she or he is supportive, dedicated, professional, and always cheerful, like the impact and the lasting impact that she or he keeps on the people that they know him. I'm really sad for your loss. May his soul rest in peace. And researchers, they don't die. They do have a lasting impact on other people.
Thank you for your kind words. Thank you.
So we'll keep it now for the questions from the attendees, either the offline or the online.
May I say some words?
Please.
Yes. I was shocked I can't speak because from your abstract, Sarka, I learned about Antonio's passed away. It was the most smiling person I saw in my whole life. You remember that when I retired, you, Violetta, and Antonio came in Alexandroupolis. Yes. Yes. And he was very active, and I can speak. I was really shocked. I sent a message to Fabrizio because also he did not tell me about Antonio's death. It is very, very, very sad thing because you see, when I met Antonio, I came to his house and in several times. A very sad thing. A very sad thing. I cannot express this neither in Greek words or not in English. I will always remember him because it was a person. He was a person who tried to find applications in several topics using hyperstructures, fuzzy sets, and so on. And also he was top in teaching and publishing, as you know, several journals in Italy. I cannot say something. Thank you
Thomas,
very much.
thank you very much. We will remember him definitely to the rest of our lives because he touched us. I was in his house, also invited various times, and both of them, they were very friendly. So I am sad, but it's life. We have to somehow continue.
Very sad. Okay.
Madeleine, I think your turn.
Yeah, I'm just, that in such situation, it is life. And we know that at the end, all of us will be gone, but you feel something, especially when someone that did a lot for his colleagues, for researchers. He tried to bridge gap between different fields of research. And I'm very happy about your talk. I know another thing about you is the gratitude. Like you have, or what do we call it here? You have this kind of other than respect. I forgot the what do I call it in English when things comes very emotional. I feel that I need to talk in my my own language, but okay, I forgot.
Dear Madeleine,
Yeah.
you are very young, but you see, in the past, for example, in this Congress I mentioned in Samothraki, there was 9 days. So there was only one talk or 2 talks every day, and then we discussed and we traveled, and it was a different connection. You see,
Yeah, life was in a
very-
certain way more connections between people. Now it's like more structured, lots of demanding in work, lots of teaching, lots of admin, lots of things. So these things we cannot do them as we used, as our parents used to do it, or you used to do it in the past.
And so it is from here and the heart. Okay.
Yeah. Any questions or comments from the attendees? Sarka, I would like to ask you a question because you've been working with Maturo on different things and closely you know him. Did any of his research or any of anything, either personal or on academic level, inspired you or changed your a certain direction in your research?
Not like you mean, but for me, I take from his research and from his approach the way to try to find applications, to try to find and to be precise in formulation for what we are doing this, for what we are doing that. You can use it like that. Maybe it will be a simple example, but it must be there some example for the reader or for the future to be able to use the definition. So this was from learned by Antonio to show on particular definition example, and if it is possible, not only one but various, because people are from various topics. So this is what I can say, maybe the most important what I take from him for my future job.
Okay, thank you. Hari Krishnan, is there any questions from the offline attendees?
Maybe
There
they
are
are
no
ready.
questions. Excuse me, there are no questions from the offline participants. Thanks to Circa for the nice talk, and thanks Madeleine for moderating the session. And I have a request to Madeleine. Today, the 3:25 to 1 second, I will tell you. 3:25 to 3:55 p.m. slot. That speaker is unwell to give the talk. Are you able to give your talk today? I have a.
Yeah, it's fine. It will be 2 p.m. here, 5 p.m. in Abu Dhabi. So 3:35, you said, right?
3:25 to 3:55.
Yeah. So it will be at 5 p.m. in Abu Dhabi. I will be in Sharjah.
Okay. Then we will schedule your session at that particular timings. So for all the offline and online speakers, please note that the Madeleine will be giving the talk from 3:25 p.m. to 3:55 p.m. Okay, now we have a lunch break from 12:40 to 2:15 p.m. in our Indian time. So once again, Circa for joining us.
Thank you and enjoy the lunch.
Thank you.
Thank you. Bye.
Thank you.
Bye. 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 See you later.
So last days, before presentation, things I can Sir is not giving a talk. We will shift this for last days, healthy presentations. Both the sessions, it's fun. I will keep it. I will send it there. Okay. Same one that connect